This is Stanford Lucy, made of over 28 million triangles rendered entirely in my own path tracing engine. And this video is the culmination of hundreds of hours spent learning and implementing systems and architecture, all to answer one question: how do game engines actually work? Because as far as I know, no one has ever put the entire journey into one long video, starting from scratch, going all the way to exporting your projects. Many people think that this is a game engine, but it's not. This is just the Unity editor. Believe me when I say this is probably the most important thing from this video. The editor should be a separate program which uses the engine as a library. But why does this separation matter? I mean, why can't everything be just one big application? Well, the answer is it can't. When you make a game using the editor and then export it, the editor vanishes. But then, if there is no editor, what takes its place? And what exactly does it do? At the heart of the engine is the application class. Its job is to coordinate all the engine's core systems, and it's special because it contains the engine's main loop, the part which drives everything forward. Right now, the loop doesn't do much, but I'm sure we'll find things to put in here. In C++, which is the language we're using here, every program starts with a main function. But our engine isn't a full program, it's a library. This means it can't run on its own. Instead, it provides an entry point header with a main function inside, which other applications can include. Think of the entry point like a small launcher. It creates the application, runs its main loop, and cleans up when done. There's a placeholder function called createApplication, which will eventually return the version of the application we actually want to run. For example, to run the editor, we create a file called editor_main.cpp. We call it main because it includes the entry point header with the main function. And down here we take the base application class and inherit from it to create this new editor class. For now, we'll keep it simple and not change any functionality. Finally, createApplication just returns our new editor class. And with that, we can finally compile the code. But sadly, the only thing staring back at us is an empty console window, for now. We'd like to see a different window, however, the actual application window, something we can look at, click on, and interact with. Opening a window on desktop isn't as simple as it seems. It's tightly tied to the operating system. Windows, Mac, and Linux all do it differently. So I started writing this window class. It might look intimidating, but for now, only two parts matter: create window and onUpdate. We'll put them to work in just a moment. Now, even though it's not my goal to support all platforms, you might have noticed this little I in the name. That's a common way of saying that this is just a blueprint, a class that defines what the window needs to do, without much actual code. And then somewhere in a platform folder, we keep versions of the window class for each operating system we want to support. Honestly, I've cheated a bit by using GLFW instead of the Windows API to make this window, but I can't be bothered. If we run the engine now, we would still just see the lonely console window. But why? We have this perfect window class, but we never actually use it. So where should it go? Do you want to have a guess? The application is the hub of all the core systems. We need to create the window in its constructor, and then in the main loop we'll add two changes. Firstly, we'll want to break out of the loop once the window should close. This happens when you click the red X in the top corner. Second, we need to update the window every frame so it stays responsive and redraws correctly. And after a brisk compilation, we have two empty windows now. Terrific. Alright, the engine is about to start managing a lot of objects, so we need a way to uniquely identify each one. Clearly, one option is to start at 0 and increment each time, but what happens when you delete an object? Do you shift all the IDs down? Or do you just leave the gap and keep counting up? The solution to this problem dates back to the 1980s, where GUIDs were originally used by the Apollo computer in the network computing system. GUIDs, or UIDs, it's the same thing, just generate a random 64 or 128-bit number. These are really large numbers, and the chance of any two IDs being generated the same is so small it's really not worth worrying about. Take just the 64-bit number for instance. It can represent more than 18 quintillion values. For comparison, there are only roughly 7.5 quintillion grains of sand on Earth. So in this little class, we are simply making a wrapper around the 64-bit number with a random generator in the constructor. I've I've done some work behind the scenes and hooked up the path tracer from the previous video into the engine, taking on the role of the renderer. We'll dive into how exactly the renderer works a bit later, but for now this leads nicely to talking about projects. You see, the renderer needs to take in a scene and loaded assets. It uses them to do a bunch of maths, usually on the GPU, and then spits out an image we then display on the screen. Now the renderer doesn't do this currently. I've just hard-coded some values so we can see something. The problem here is all the scenes and assets need managing. But what does that even mean? What even are scenes and assets? Back in the code, I've created this project manager class. We'll give it a few basic methods like new, open, save, and close project. And to keep things organized, we'll also split the rest into two subsystems, the scene manager and asset manager. But before we dive into more code, let's look at what this really means in practice. Here in Unity, we have the assets panel. That's where things like textures, models, and materials live. These are our building blocks. And then we also have scenes here, which are basically just containers for the stuff we place in the world. Inside the hierarchy, we can make a new entity, say a cube, and over in the inspector, we can add components to it, like a mesh renderer and a material. Very briefly, this is the idea of an entity component system. An entity on its own does nothing. Components are what give it functionality. Just to be clear, we are not building the editor UI just yet. We are writing the functions that the UI panels will call later on. So I've put together a simple scene manager class. It can create and delete scenes, and of course it can also keep track of whichever scene is currently open. Now, what exactly is a scene? In our engine, a scene is basically just a container of entities. Inside the scene, we can create and destroy entities, and under the hood, all of that is powered by a library called ent. You can think of this registry here as a really fast map that links entities to the components they own. Speaking of components, every entity gets an ID and a tag component. After that, it is up to us which components we give it. A transform lets us move, rotate, and scale it. If we give it a mesh and a material, it suddenly becomes something we can actually see. We can even add a camera component to turn it into a viewpoint. When we call create entity on the scene, it gives us back a little handle. This handle is our way of talking to that entity. We can add components, check what it has, or remove things if we need to. Of course, it wouldn't be very useful if we couldn't save and load our scenes. So in here, I'm simply looping through all of the scene's entities and their components and writing them out into a file. We are using the LR-scene extension for our scenes. As for the format, JSON is probably the most well-known. But for this project, I've gone with YAML. The exact details aren't all that important. What matters is that we can store everything in a text file and then bring it back later. With that foundation in place, let's move on to the asset manager. So the question is, how do we actually get assets into the engine? I've created this import asset method. The way it works is it takes a file path, peeks at the extension, and then decides, is it a mesh, is it a texture, or maybe some new type of asset we'll add in the future? Based on that, it just calls the right loader. But importing is only half the story. We also need to keep track of everything we've brought in, and for that we have the asset pool. Think of the asset pool as one big container where we are piling in all of our meshes, textures, and whatever else. And the beauty of having them all together like this in a single struct is that we can just pass around the pointer to it. The renderer, for example, doesn't have to go hunting for all the scattered collections, it just gets the pool and knows exactly where to look. Inside the pool, the first thing you'll see is the metadata. This is just a map connecting an asset's ID with the information about it. For meshes, that means things like where in the big triangle buffer does the mesh start, how many triangles does it have, and some info about its bounding volume hierarchy. I've talked about these acceleration structures in the ray tracing video. Textures have a similar setup with their own big buffer. So the asset manager loads assets straight into the asset pool, and the renderer then dips into the asset pool to render a frame. Now, of course, there is a big problem with this. The assets can be anywhere on the computer. If we just saved the project and came back tomorrow, the engine would have no clue where to look. That's where metafiles come in. For every asset we import, we create a small metafile in the project folder. It stores things like the asset's original path and, crucially, its unique ID, because those IDs are randomly generated. Without storing them, we would never be able to match things up the same way twice. So if you have, say, 2 meshes and 2 textures, when you hit Save Asset Pool to Folder, you'll end up with 4 meta files. Then the next time you load the project, the manager just reads those meta files, reloads the assets, and everything lines up perfectly. And that brings us back neatly to the project manager, which sits above all of this. Its job is not to deal with meshes or textures, but simply to tie everything together. But how does it know whether a folder is a project? Well, it looks for a file ending in lrproch. If there is one, the folder qualifies. Creating a new project just means making a new folder, writing that project file, and then setting up both the scene and asset managers. Opening a project works the same way, but in reverse. We check that the folder contains the project file, and if it does, we load the asset pool back in. Saving is equally as simple. If there is a project open, we save the project file along with the scene and asset data. And closing, that's just resetting everything so that the editor is ready to open something else. Now, before we jump into the editor UI, there is something we need to address. We've been adding more and more systems into the application class, and it's starting to get messy. To organize this, we'll introduce something called a layer stack. The layer stack splits the engine's main loop into multiple layers. Each layer follows a simple blueprint. We can call onAttach, onDetach, and onUpdate. When you add a layer to the stack, it always goes on top and calls its onAttach method. When you want to remove a layer, you always have to start at the top, and before the layer gets removed, we always run its onDetach method. The layer stack itself has an onUpdate method, which is called every frame and updates the layer in order from the topmost to the bottom one. In the code, I made this iLayer class, which again has this little eye telling us that this is just a blueprint for what a layer needs to do. You've seen the methods already. The stack just calls them at the right time. So let's add our new layer stack into the application class. In the main loop, we'll call LayerStack onUpdate every frame. Below is the renderer render, so let's clean it up into its own layer. Here I've just created the new layer, which calls render in its onUpdate method. With that, we just push the layer onto the layer stack and we are done. Now, this may not seem very useful at this point, as we've written like 10x more lines to do the same darn thing, but here's where it gets interesting. Up until now, everything we wrote, except this one editor file, was the engine library. And even in this single editor file, we are only using the application class and running it. Initially, we didn't modify the application class in any way, but now that we have the layer stack, we can quite easily push an additional layer onto the layer stack from here. And this will allow us to write code which we know will get executed in the main loop every frame thanks to the onUpdate function. What I really want to drive home is that we are not changing the engine library right now. We could just as easily make another application, perhaps the one I've hinted at in the intro, which uses the engine in a completely different way. Alright, let's zoom in on the editor layer we've just added. It's sitting right on top because it's the last one we've pushed onto the layer stack. So what does it do? Its job is somewhat similar to the project managers, as it just ties all the panels together. And because this layer will be massive, by far the biggest one, we need to think about how we want to structure it. Each panel will live in a separate file, and to keep them somewhat uniform, we have this iEditorPanel class, again serving as a blueprint for all the other panels. Every frame when the layer stack onUpdate is called, the editor layer updates the panels in no particular order. And we know that each panel has an update method because it is required by the iEditorPanel interface. In code, it's super clean. We keep an array of panel objects. In the constructor, we spin them up, drop them into the array, and that's it. When update time rolls around, we just loop through and fire off their update methods. And for the UI itself, I'm sticking with imgui. I've used it before, you've seen it in the last video, so let's keep rolling with it. For starters, I made this dock space where we'll be putting all the panels. And logically, the first panel we should add is the viewport. What we basically need here is to display what the renderer sends us on the screen. But the problem is the window can be resized, and the texture size will most likely not fit. So we have a few choices. We can either stretch the texture to fit, but then we lose the aspect ratio. We can maintain the aspect ratio and maximize its size, or another option would be to keep the original texture, center it, and crop any excess. So why not do all three? Most of the viewport panel is just math for resizing the texture. The rest, and honestly the more interesting part, is how we actually receive the texture from the renderer, and it's tied to something I've kept from you until now: the event system. Each layer, including the panels within the editor layer, have an additional function, onEvent. On top of that, each layer has access to an event dispatcher, which is secretly just the LayerStack with limited functionality to only allow sending events. So when a layer decides to dispatch an event, the LayerStack calls the onEvent method, passing in the event to all layers starting from the top. Sometimes a layer might want to prevent the LayerStack from dispatching the event further, so what the layer can do is to consume it. The LayerStack actually always first checks if the event is consumed, and only if that's not the case, it proceeds to send it further. And for the curious minds, the iEvent class comes with consume and isConsumed functions, and then every event in the engine stems from it. For instance, we have input events. These are actually sent by the window class and include keyboard events. We have mouse button presses and releases, moving the mouse, even scrolling the scroll wheel, all trigger events. On top of that, we have a window resize event, but the one we are actually after is the new frame rendered event. This event is only sent by the render layer, and our viewport panel receives it. It carries the texture the renderer generated, and that's what we then work with. So here it is, the viewport panel. Now notice something, it doesn't really depend on any other panel. Of course, right now there is no other panel, but that just kind of proves my point. In the future, some panels will need to talk to each other and share information. So we need a clean system to do this across the editor. So I threw together this little struct called editor state. Right now it's split into two parts, temporary and persistent. The persistent part is for values we actually want to keep around even after closing the editor. For example, the viewport panel uses it to remember the viewport mode you last had selected. And of course we need to write the persistent part into some file for this to work. Once that's in place, we can just hand a pointer to the editor state. It's basically the same idea as how we pass around the asset pool in the engine. But here's the catch, not everything should go through the editor state. To show this in action, I actually put together a scene hierarchy panel. Right now it's very basic, it just loops through all the entities in the scene and lists them out. When I click on one, it marks the entity as selected. I also added a tiny add entity dropdown. Clicking it just creates a new empty entity and drops it into the list. And this is where the editor state steps in. Whenever we have an entity selected, its ID gets written into the temporary part of the editor state. That way, maybe another panel, say an inspector, could one day grab the ID and show all the entity's components. But coming back to the bigger point, the actual scene itself is not stored in the editor state. Instead, we fetch it from scene manager getOpenScene. But why not just keep it in the editor state? I mean, it just seems a lot more convenient that way. Well, the answer circles back to the intro. Once we export the game, the entire editor disappears. And with that comes also the editor state. So if we kept the scene there, the mysterious engine component would have no idea which scene to render. Since the scene manager is part of the engine library, we can safely store the scene there instead. Alright, since I've kind of heavily hinted at the inspector panel, I made this little class. I don't think the code here is all that important, but we simply look for the selected entity using the ID from the editor state and then loop through its components. The remaining like 95% of the code is just IMGUI shenanigans to make it look nice. But I'm sure you'd rather see the panel, so here it is. But listen, we've hit a bit of a snag. I can't add a mesh to this component since we need the assets panel for that. So I've started writing this bit of code. It's decently long, again. I don't think it's all that important. We are basically just calling the functions of the asset manager and giving them buttons. I decided to split the panel into two sections. On the left we have asset tiles like the mesh tile, scene tile and a texture tile, and on the right side we have the details area, which shows information about whichever tile is selected. Honestly, I'm getting really desperate to get something on the screen, and unless we want to see a pixelated mess, because that's just how the ray tracer works, I'm gonna add a render settings panel which controls some things about the render. We'll come back to this later, hopefully. Let's just make some scenes now. Alright, I'm happy with how this turned out, but I've just realized we cannot save our precious work. And there is another problem. I've been tactically cropping out the title bar, but poor thing, it's trying its best. I mean, let's give it a proper menu bar, just like all the apps that you know what they are doing. Well, it sounds simple, but it really isn't. The library we are using for the window is called glfw, and unfortunately it doesn't support custom title bars. What I do find quite fortunate is this Cherno's video, so I forked his version of glfw and integrated it to the engine. After like 2 days of work, this is what I've come up with. Now, I know for a fact that this is still a bit buggy, so I don't guarantee this will work on your machine, but we've got this file menu. On the right side we have the breadcrumb displaying what project and scene is currently open, and of course the standard buttons. Fun fact, these are code icons, which are the same icons Chrome and VS Code uses. By the way, since we are already on this topic, all the other icons are from a font called Font Awesome. But let's not ignore this play button right here. Now in Unity or Unreal, hitting this means you want to simulate the game you've made. Scripts run, physics is active, in-game UI becomes responsive, but we don't yet have most of those things. What the play button really does is it switches the scene manager into simulation mode. In this mode, the scene manager makes a copy of the open scene, and anything that happens to this scene during simulation is erased once we exit. Now, when we are in simulation, the renderer uses a different set of settings, and this allows us to work in lower quality, but then make high resolution renders when we click the button. Another useful addition to our engine would be a panel where we could see, how well or terribly our engine is doing. In other words, we need a profiler. At the heart of it is something called the scope timer. Its whole job is to start the stopwatch when it's born and stop it when its destructor is called. It then finds the difference in time and slips it straight into the profiler's stash. Using this, we can get the current FPS by just making a scope timer in the beginning of the main loop. Now, of course, this isn't very useful when we cannot analyze what it measured, so I made this little profiler panel, where each line in this plot shows a different scope timer. If we want to zoom around, we can just disable this auto fit button. At the top we've got FPS and milliseconds per frame. There are a bunch more things like pausing, clearing the buffer, tweaking the colors and so on. But all of this looks a little bland, right? I mean, what if this is how you roll? Well, I've added a themes panel. In the color editor section, you can change the individual colors, and here the theme can be exported and loaded back again. The path to the theme file is stored in the persistent part of the editor state, so it stays between launches. Speaking of launches, let's make a launcher window. It has like 2 buttons, which let us create and open projects. When it comes to creating a new project, I've actually spent a bit of time doing input validation. Alright, I know I haven't spoken much about the renderer, and that's because we didn't really have all the necessary building blocks for it to make sense. But let's now take another look. In our engine, instead of a traditional rasterizer, we have a path tracer. It's worth noting that the whole engine is still evolving, so keep that in mind as we go along. If I bring up the renderer class, the render method is what converts the scene and asset pool into a texture we then draw on the screen. However, this method itself is split into smaller functions, which run in sequence. We are outsourcing the work to the GPU, specifically through OpenGL at the moment, and we are running a compute shader from the previous video which does the path tracing. But the main question is, how do we take the scene and assets and send them to the GPU? Well, it all starts with this parse function. It filters out the entities in the scene that actually need rendering. In other words, we only draw entities which have a transform component, a mesh, and optionally a material. If an entity doesn't have a material, we assign it a default one. Now all of this only happens if we have at least one camera in the scene to render anything. If we have something to render, then this method, setup GPU resources, takes control. It takes the parsed scene and asset pool and sends it to the GPU. The only catch is that we want to minimize unnecessary uploads if the buffer did not change. So here's the trick. Every array in the asset pool has a version number, and if the renderer's version matches, we skip the upload. If not, we update and increment the version. Finally, we just dispatch the shader and let the GPU do the heavy lifting. So right now, we have most of the basic tools an editor needs. We can create scenes, open and save projects, see the performance, but there is still one feature missing, arguably one of the most exciting ones. And that's exporting our game. Remember the mysterious engine component? Well, it turns out to be the engine runtime. Say we want to run the game without all the extra stuff. What do we actually need to do? Well, it turns out we just need to load the project and display it on the screen. Both of the tasks just require the project manager and the render layer, both of which are part of the engine library. So all we really need to do is create a new runtime application and push a runtime layer onto the LayerStack. This runtime layer will be much simpler than the editor layer. No panels, no fancy buttons, just one big viewport. It will listen to the new frame rendered event, which the render layer produces, and stretch the texture to fill the entire window, similar to how the Viewport Panel does this. Now, this doesn't sound very difficult, does it? So what's the catch? Let's look at the ideal workflow. I've added an export option that just opens this window. Here we can set the name and folder where we want to save the exported game. The tricky part comes when you realize we somehow need to generate a runtime application in that folder, right? So that you can just click the executable and the game starts. But how can an editor generate an executable? Well, the trick is it doesn't have to. The runtime never actually changes between games. And that's the crucial idea. We simply pre-compile the runtime once and store it in a known location. Then, when it comes time to export, the editor just copies it into the destination folder. But how does the runtime know which project to run? The simplest solution is to copy the whole project, which we are already doing anyway, into the destination folder and tell the runtime to run the project next to it. Of course, there is one more wrinkle: resources. Fonts, shaders, models, textures, anything that the game needs that isn't code. When you build an installable game, we want it packaged in a way where you just send the folder to a friend and it just works. And if you recall the asset manager, we have these meta files which point us to assets all over the file system. What we need to do is we need to find all these assets, copy them into the destination folder, and update the meta files, which have been also just copied here, to point to these new assets instead. It sounds minor, but hearing this would have saved me tons of time, honestly. But after all that, now I think is a good time to test everything out. After hundreds of hours on this project, finally seeing this window feels really rewarding. And honestly, I just want to say thank you. This channel has grown from 0 to over 5,500 subscribers since the last video, and that's entirely thanks to you guys. The whole code is up on GitHub, it's free, I gave it an MIT license. Again, thanks a lot for watching, and I'll see you next time.